Welcome to The Explainer. Today, we're going on a journey, and it's all about learning to think in code. We're going to trace the path from the simplest ideas all the way to some really powerful programs. The goal here isn't just to learn how to code, but to really get into the mindset of a programmer. So let's dive right in. And you know what? We're not even going to start with code. We're going to start with an idea. Think about it. There's a huge difference between knowing what something is versus knowing how to actually do it. And that right there, that's the heart of programming. It's all about that how-to knowledge, creating a recipe, basically, a step-by-step guide that a computer can follow perfectly. And this is so fundamental. I mean, really think about this quote. At the end of the day, a computer only does two things. It calculates stuff and it remembers the answers. That's it. Every single thing a programmer does, no matter how mind-blowingly complex it seems, just boils down to telling a computer how to do those two simple things over and over at incredible speeds. All right, so let's get into our first section. This is the foundation, where it all begins. We're talking about a new way of thinking, something called computational thinking. And trust me, this is the bedrock for everything else we're going to cover. Okay, so let's break down that distinction we just talked about. On one side, you've got declarative knowledge. This is just stating facts, like the square root of x is a number y that, when multiplied by itself, equals x. Cool, we know what it is. But on the other side, you have imperative knowledge. This is the good stuff for us. This is the how-to, the actual recipe for finding that square root. In programming, it's all about mastering that imperative side, about turning a factual problem into a step-by-step process the computer can actually execute. Okay, so we've got our recipe in mind. The next logical step, right? We need a language to write it down in. And that's what this section is about. Learning the grammar, the absolute fundamental rules of a programming language. So first things first, the most basic building block you'll ever use, the variable. The best way to think about it is just like a labeled box. You give it a name and you put a piece of information inside. That's it. This is how a program remembers stuff, tying right back to that core function we talked about. And I love this quote from Shakespeare here because it makes such a great point. To the computer, a variable named X and a variable named user age are exactly the same. It does not care. But for us humans, oh, it's a world of difference. Choosing good descriptive names is absolutely critical for readability. It's about being kind to other people reading your code, and honestly, being kind to your future self when you come back to it 6 months later. All right, next up, operators. If variables are the nouns, the things, then operators are the verbs. They're the action words. These are just the symbols, like the plus sign or an equal sign, that tell the computer to actually do something, to perform a calculation with the stuff you've stored in your variables. Okay, now this is where things get really interesting. This is where programs start to feel smart. We're talking about branching. A branching program can actually make decisions. It uses what's called a conditional statement, which is basically just a simple true or false question. And based on the answer, the program can go down different paths. This is what makes software feel dynamic and responsive. Okay, so we've got the basic grammar down. We have variables, operators, and we can even make decisions. But how do we go from these simple building blocks to creating really complex software? Let's talk about the toolkit. And the biggest tool in it is something called abstraction.
And this really is the million-dollar question for any programmer, right? How do you manage complexity? How do you look at a problem that just seems impossibly huge and not get totally overwhelmed? How do you even start to make it manageable?
Well, the answer is a super powerful concept called abstraction. And this analogy is just brilliant. You have to love it. Abstraction is all about forgetting the details you don't need right now. It's like a parent giving a super long, detailed instruction, and the teenager just hears the main point. Yes, it's the art of ignoring all the noise to focus on what actually matters. So how do we actually use abstraction in programming? Well, we use a classic strategy called divide and conquer. It's exactly what it sounds like. You take a big, scary problem and you break it down into a bunch of smaller subproblems. The key is that these little pieces have to be easier to solve. Then you solve each little piece and you combine those solutions back together to solve the original big problem. Simple, but incredibly effective. All right, so we've got the tools to build some pretty complex stuff now. But here's the catch. The real world isn't neat and tidy like a math problem. It's messy, it's unpredictable, it's uncertain. So the next big question is, how on earth do we get our programs to model that? Well, one of the coolest ways to do this is with something called a Monte Carlo simulation.
The idea behind it is actually pretty simple. You can't predict a single random event with certainty, right? But what you can do is run a simulation of that event over and over again, maybe hundreds, maybe thousands of times, and then you just average the results. It's a way of finding the most likely outcomes in a sea of randomness.
Let's take a simple coin flip. If you simulate flipping a coin just 10 times, you could get a result like this, say 7 heads and 3 tails. Looking at that, you might think, is this a trick coin? The result seems pretty random, pretty uneven. But now, check this out. Look what happens when we run that same simulation, not 10 times, but 100,000 times. Suddenly, the law of large numbers kicks in. All that random weirdness from a small sample size just cancels itself out, and the results get incredibly close to the true 50-50 probability we all know. It's amazing.
And that brings us to the final stage of our journey. You could call it the frontier. This is where things get really wild. It's the point where we stop giving the computer a very specific step-by-step recipe, and instead, we start teaching it how to figure out the recipe all by itself.
And of course, we're talking about machine learning. That's the essence of it, right there. It's a fundamental shift. We go from writing explicit instructions for every single possibility to writing programs that can look at a bunch of data and discover the patterns and the rules for themselves.
So how does that even work? Well, it all starts with data. We have to take things from the real world, like, say, the number and type of teeth a mammal has, and we have to convert them into a list of numbers. In the biz, this is called a feature vector. It's how we translate messy, complex reality into a structured language that a computer can actually work with, compare, and learn from.
And once you have that data, machine learning generally goes down 2 main paths. On one hand, you have supervised learning. Think of this like being a teacher. You give the program a bunch of examples that are already labeled, like, this set of teeth belongs to a carnivore. The goal is for it to learn the rule. On the other hand, you have unsupervised learning. Here, you're more like an explorer. You just give the machine the data with no labels and say, go find interesting patterns or groups in here on your own. Both are incredibly powerful. So when you boil it all down, what's the big takeaway? Learning to program, it's really not just about memorizing a bunch of weird syntax. It's a journey. It's about learning a completely new way to think, a way to look at a huge problem and break it down, a way to manage complexity, and a way to find patterns you never knew were there. This whole idea, it's like a map for thinking in code. A map you can use to solve just about any problem, anywhere. So the only real question left is, what problems are you going to solve with it?